Okay, so I will be talking about a coherent mechanical oscillator driven by single electron tunneling. And before I start, let me thank my funders and the people who worked on this paper, in particular Yu Tian Wen, who was the student who did the main experiment that I'll talk about here. So when I say an oscillator, what I mean is some nanomechanical object that, as well as being a resonator, which moves in response to an oscillating force, is also an oscillator in the sense that it generates an oscillating motion in response to a DC drive. And the device that I will talk about is a suspended carbon nanotube, as shown in this picture in the background here. And what we were able to measure is that by flowing a current through this, a DC current, we could excite oscillations of the nanotube, and we were able to measure them and to test their coherence and to explore an interesting analogy between the physics of this system and the physics of the laser. So why are these kinds of devices interesting? Well, all of us, or many of us in the field of nanomechanics, are trying to use mechanical resonators to detect very small forces and small amplitude motion. And one way to do that is to use a single electron transistor, which is a transistor whose conductance depends extremely sensitively on its charge. So what you can do in a carbon nanotube or in other kinds of mechanical resonator is to integrate a single electron transistor either into the moving elemental cell itself or nearby in such a way that when the resonator moves, the displacement changes, therefore the electrical potential changes. And if you can make the current depend on the electrical potential, then you can use this to distinguish displacement in one direction versus displacement in the other direction, because for an upward displacement, you have a large current, and for a downward displacement, you have a small current. And many groups, I've listed some of them, many groups are working on this kind, on devices similar to this because of the very high sensitivity that we can expect. But there is an obvious question that arises from this, which is what about the force of the electrons tunneling through the single electron transistor? Because those two, they must have some back action on the object being measured. The back action comes because of the electrostatic force between the electrons and the gates. And how is this back action going to disturb the thing that you're trying to measure? That's the motivation for doing this experiment. And the particular disturbance that we are able to measure is that the single electron tunneling sets up a coherent oscillation of the mechanical resonator. So let me talk now about our device. So this is a cartoon of a carbon nanotube electromechanical sensor. So what you can see here, this wire here is the carbon nanotube. It's a rolled up sheet of carbon, maybe 3 nanometers wide or so, depending on exactly how it's grown. And if you suspend the central part, then it will vibrate. And you need to be able to measure that, of course. So what you want to do is to incorporate this into an electrical circuit. So what we do is to, these 2 green blocks here are our metal electrodes. And what we can do is we can source a voltage between the 2 sides here and measure the current that flows through the nanotube. And what we hope is that when the displacement changes, the current will change too, and that's a way to measure it. Now we do more than that, because what we also do is we want to be able to control the mechanical resonator. And so we have gates also in our devices. We normally have a few of them up to, I've drawn 3 here. And there are different things that we can do with these. So the first thing we can do is to actuate the motion. If we send in an oscillating voltage on one of these gates, then this excites the motion, and this lets us drive or read out the mechanical frequency. We can do more than that though, because we can apply a DC voltage, and with that DC voltage we can adjust the tension on the nanotube because the electrons on the nanotube will pull it towards the gates, and that can change its frequency a little bit. And then finally, we can use these gates to control the electrical potential along the nanotube. And if we choose a semiconducting nanotube, then that means that we can dope particular regions to contain electrons or holes, or to tune the tunnel barriers between different conducting regions of the nanotube. So this is the device as we plan to make it. This is a picture a few years old now of one from my postdoc, where you can see quite faintly here, this faint white line here is the carbon nanotube, which shows up faintly through the electron microscope. Here are the metal electrodes on either side, and then underneath, in fact, partly buried underneath some oxide in this particular device, are the gates that we use to control it. And the reasons to use, you can realize this kind of device, this kind of suspended nanobeam from other materials as well, of course. But the advantage of using nanotubes, the main advantage is that they are, well, the diameter is extremely small. So that means that the mass is low, which gives you a high frequency. So that's nice because it lets you operate in the radio frequency measurement regime. It's also interesting because the mechanical frequency, if you convert it to a phonon energy, is quite close to the temperature of a dilution refrigerator, which means that you have some hope of accessing a few phonon states and preserving them. Also, we know, thanks to a lot of work from many people on fabricating high quality nanotube devices, if you can make the surface of the nanotube extremely good, you can reach a high quality factor. So quality factors of several thousand are now routine, and they can in fact be much higher. So that's nice because it improves the force sensitivity. They're mechanically compliant because they're so small, and they're also semiconductors, and in fact they can even be Josephson elements as well. So these are all nice features and the reasons to explore interesting physics of nanomechanics with these very light nanotube resonators. How do we make such a device? We want the way that nearly all nanotubes in electronic devices are made is by catalytic growth. So there is a process of chemical vapor deposition in which you deposit catalyst on the surface of a chip and you heat it to a high temperature of 900 degrees in the presence of methane and hydrogen. And there's a chemical reaction in which, if you choose your catalyst correctly, the methane gets cracked, and from the beads of catalyst, nanotubes will fly out through the gas flow. So the way that we do this, our particular implementation, is to take a quartz chip with some pillars on it. On top of the pillars, we deposit some catalyst, and then the nanotubes grow. And this, we find, makes fairly high quality devices, as we know from the mechanical quality factor and the electronic properties. Unfortunately, we can't image the nanotubes in our devices themselves, but what I do have here is a picture made by my former colleague Jamie Warner in Oxford, who was able to image a nanotube made in a different way. But what it does show is that these nanotubes really, they can be almost atomically perfect under the right conditions. And so this gives us a good reason to believe that in our devices as well, they may not be as clean as this, but certainly we can hope that the level of surface contamination may be quite small. Now, in order to benefit from this beautiful chemical assembly, then we need to be able to incorporate the nanotubes into a device without contaminating them. And this makes lithography difficult, of course, because when you spin resist on a nanotube, probably it's very hard to remove every single resist molecule afterwards because the resist is very sticky. So there's been great work over many years on how to make very clean nanotubes by incorporating the nanotube into the device as the very last step. And the particular way in which we do this, we didn't invent this, there's previous work from other groups, but we do stamping in which we have two chips. One chip is the device chip on which we fabricate contacts and electrodes, and the other chip is the growth chip on which we grow the nanotube. So any lithographic residue is going to end up on the device chip, and we mostly clean it off. The nanotube itself is almost pristine. Then we take these two chips and we align them in a mask aligner and bring them together. And if there is a nanotube, which relies on luck, but if by luck a nanotube is growing between two quartz pillars, then it will get transferred to the device chip, and we can detect that by probing for the electrical conductance between the two contacts on either side. So this is it's not a deterministic process. It relies on the nanotube growing between two quartz pillars, and then the stamping itself doesn't always work. But we can make 100 or so devices in parallel, and if we do this, particularly over a few chips, then we are able to get high quality mechanical resonators. So this is how it works. This is what the device looks like. So this is an optical image on the left here, where you can see the bond pads and the wires running into the device. This particular device has two gates per nanotube, and this is a high optical magnification. You can faintly see the electrodes here. You can see catalyst residue on either side from the stamping, and then this is a different device. It has a different number of gates, but you can see here's the nanotube lying between the source and drain contacts. And if the nanotube looks a bit thick, it's because in this device, then in order to make it visible through the microscope, we coated it with some extra metal. Otherwise, it barely shows up in the micrograph. So the outline of this talk, I talked about the motivation for doing electromechanics with carbon nanotubes and how we make them. But the main part of this talk is going to be about the physics of carbon nanotubes operated as electromechanical sensors, and how then we measure and characterize a nanotube mechanical oscillator. So the first challenge is how we measure the vibrations of this device. And the challenge, of course, is the device itself is quite small, and the vibrations are typically very small as well. So you're trying to measure a signal, you're trying to measure a displacement that is on the order of picometers. And to do that, we take advantage of this excellent amplification offered by a single electron transistor. So this is how it works. So here is a nanotube spanning across a trench. The middle part is free to vibrate. And a nanotube is generally a semiconductor at low temp. So there will always be some band gap, almost always there'll be something, because of even if no matter what the crystal structure is, there will always be some strain or torsion or something we find that means that there's going to be a gap. So because of the gap, that means that we can control. Well, that means that there are going to be regions that are conducting and regions that are not conducting. And by a combination of the Schottky barrier at the interface and by tuning the gate voltages, then we can tune the potential so that the central part of the nanotube is conducting. It contains either electrons or holes. And then on either side, there's a barrier. So we have here a quantum dot, which has Coulomb blockade, and therefore we can operate it as a single electron transistor. So what that means is if you plot the chemical potential in the leads on the left and the right, and on the island, the central part in the middle, then inside the lead you have a continuous density of states, so all of the states are filled up to the Fermi level. But inside on the island, then every electron you add, you have to pay a penalty of a charging energy. So the chemical potential goes up in a ladder of levels, something like this. When you change the gate voltage, what you're doing is you're changing the potential on the island, so this whole ladder moves up or down. So you can switch yourself between two configurations. In one configuration, there is an available level between the Fermi levels on the left and on the right. That's this one here. In the other configuration, there is no level available. So what you find as you change the gate voltage is that the current through the nanotube oscillates in this semi-regular pattern here, where the peaks correspond to a level in the allowed window, and the dips correspond to no level in the window. So every time it goes through a cycle, this corresponds to adding 1 electron to the island. And you can see now that this is a transistor. It's a transistor because its conductance depends on the gate voltage. And it's a single electron transistor because the entire cycle of being turned on and on again corresponds to 1 electron being added. And what this means, because it relies on single electron charging, this slope here is pretty steep. And so a small change in potential will give you a large change in current. And that's something that we use for detecting the motion. We do that, well, to see that, you could replot, if you plot this graph here of current versus gate voltage, you could imagine that you can't directly measure this, but you could replot this versus displacement instead of against gate voltage, and you'd have the same dependence because the potential depends on displacement in the same way. And so now when the nanotube moves, then the potential changes, and so the current moves itself up and down this slope here. And so what you should see, if there is a vibration, is you should also see a change in current. And that current at any moment is going to be proportional to the instantaneous displacement. So that's what we set out to measure. The difficulty is the current is quite small. So the current you can see here, it's only picoamps, and it's changing very fast. It's a radio frequency current, as I say. So we had to do a certain amount of electrical measurements to be able to detect that. But this is roughly our circuit, or this is a simplified version of our circuit. Here is the device. It's sitting at the bottom of a dilution refrigerator. This is the gate through which we excite it. So we send in some drive tone here to start it moving. We apply a DC voltage bias across the nanotube so that a current flows. And then we want to measure 2 components of this. So first of all, we want to measure the DC current, the average current, which we do by standard low frequency current measurement technique. But then we also want to be able to measure the high frequency component as well. And so we needed to build a radio frequency amplifier chain inside the refrigerator. We used, in fact, we find that we used both a commercial transistor amplifier, and then we also found that using a squid amplifier as well helped our sensitivity. To separate the DC and the radio frequency current, we used this circuit here, which acts effectively as a bias T, so it sends the RF current, the radio frequency current this way, and the DC current goes the other way. And then we also tune it so that it resonates, which helps because it helps to transform the impedance between the high impedance of the nanotube and the lower impedance of the amplifiers. So using all of this, the key point is that the output signal here, the one that contains the most interesting information, is a voltage that is going to be proportional to the instantaneous displacement of the resonator. So any resonance or oscillation here, we expect to be able to see in the output voltage. So the first thing to do is to find out whether this device really does act as a resonator. And to do that, then we measure the power that comes out using a network analyzer while we drive it using the gate. And what we find is that if you hit the mechanical resonance frequency, in this case it's about 179 megahertz, then you get a peak in the power that's coming out. And that tells us that we've excited the nanotube. And from the width of this, we can work out the quality factor. And by comparing the height of the signal here to the noise in the background, then we can also calculate how what our imprecision is in measuring the displacement. And there is a good deal of uncertainty here because we don't know precisely the mass of the nanotube, we don't know precisely its length. but we can estimate that our imprecision is certainly not worse than 5 picometers per square root of hertz, which is not too far away from, in fact, the best that you can do, the standard quantum limit, that the best that quantum mechanics allows for a continuous measurement. So this isn't world-beating, but it certainly is a sensitive measurement of the nanotube's vibrations. So if the nanotube is oscillating, then we should be able to detect that. And that is what I'm going to do in the last part of this talk. So let us say, first of all, why might we expect oscillations? The reason is we have a combination of two things in this device. We have the single-electron transistor, which is approximately a two-level system because at any moment it's either charged or not charged with an electron. And then we also have the resonator, which has a sharp density of states close to its mechanical drive frequency. And we expect some coupling between these two because the electrons on the island apply a force that is going to excite the resonator. So if there's some kind of feedback between these two things, then we expect that the current flowing through the two-level system will disturb the resonator, and maybe it will even set up a feedback loop that will make it oscillate. And this is the question of whether it really does oscillate is an old one, both experimentally and theoretically. It has been suggested that you may, this combination of a two-level system, a single-electron transistor plus a resonator, may act as a kind of phonon laser. In a laser, you have a two-level system combined with a microwave with an electromagnetic cavity. In the first experiments, that was an ensemble of two-level systems, in fact, an ensemble of molecules. Can you do the same thing with sound? And this question was considered at least as long ago as 2007 in this pair of theory papers, in which they said, well, many of the things that you need for a laser also exist in a mechanical resonator. You have a boson field, the phonons are that boson. You have a two-level system, the single-electron transistor. You don't have a cavity directly, but you do have a resonator which confines the phonons and acts in the same way. The ingredient that you're lacking, though, is stimulated emission, because there's no degeneracy, there's no sharp level splitting in the single electron transistor that can coincide with the frequency of the resonator. So what these papers discuss is that you can set up something that's equivalent to stimulated emission in this system here, and I will explain that in a moment. But let me first tell you how we identify a coherent oscillator in this device. The first thing we did to look for that is to not excite the device at all. We're simply doing a standard conductance measurement as a function of the bias voltage, the source drain voltage, that is, on the vertical axis, and the gate voltage on this axis here. And what we see, if we are low bias, then we see a pattern of the conductance turning on and off, which is exactly what you expect for a single electron transistor, for the reason I told you earlier. As you increase the bias voltage, then you see this diamond pattern, which again is completely standard. It's a little bit irregular, that tells us we have some disorder, but it's basically what you would expect for a single electron transistor. What is not what you would always expect, what I've chosen the color scale to highlight, is we see these sharp jumps, these sharp peaks in the differential conductance, which means sharp jumps in current at high bias. And this suggests that under certain conditions, the device is going through some kind of threshold, possibly a transition to oscillation. The second experiment was to sit at a fixed bias of 2.5 millivolts. So we sit here, and again, we change the gate voltage, and now we're driving it. So depending on what frequency we drive it, then we may hit the mechanical resonance frequency. And if we do, then the motion becomes large, the voltage out becomes large, and so we get a peak in the transmission between the drive and the output. So these bright lines here are the mechanical resonances of the device. And you can see they depend on gate voltage in this regular pattern here, which tells us that the mechanics the mechanical frequency is being affected by the charge state on the single electron transistor. So there's some coupling between them. Okay, this is mechanical resonance. It's been seen many times before. Mechanical oscillation is when you don't drive it, do you still see an output? And indeed we do. So what we're doing in this third experiment is to turn off the excitation. So the resonator is doing whatever it's doing. We're still flowing a current, and then we're looking at what comes out. And what we see is that once again, we get a peak in the emission power at the particular frequency that corresponds to the resonance frequency that we measured in the panel above. So what this is telling us is that it is generating some kind of motion, of oscillation, stimulated by the current flowing through it. So that's very promising, but it's not enough to show that it's the analog of this phonon laser that we're looking for. To do that, we have to show that it's a coherent source as well. So what defines a coherent source? A coherent source is something that emits with a well-defined frequency and a well-defined amplitude as well. And if you read books on quantum optics, as we did, then the way to distinguish the coherent emission of a laser with the incoherent emission of a filtered light bulb is to separate the emission into in-phase and quadrature components, to plot those against each other. And for the laser, it will go around in a circle like this. For an incoherent source, then it will wheel around in this random way. And so that's what we set out to look for. We did a heterodyne demodulation technique that separates out the emission into the sine component essentially and the cosine component. And we digitize both of those. And indeed, you can see this is what the signal looks like. So both of those are wiggling, and you can see that although there's clearly some fluctuations, there's also some stability in the amplitude and the frequency. And we can become quantitative about that. There's two things we can do. The first thing is to plot a histogram of the in-phase versus the quadrature component. Below threshold, you get this blob at near zero, which tells us that it's a quasi-thermal source. This is what you would get by just looking at some black body radiator. Above threshold, though, you get a ring. And that's the indication of coherence. What it's telling us is that although the phase may be fluctuating slowly, the amplitude stays at some fixed value. So that's a coherent oscillator. And then we can also look for the phase coherence by plotting the autocorrelation of this signal versus time. Below threshold, the phase memory dies immediately. The autocorrelation function goes very quickly to zero. But when you're above resonance, then there is a long-lived memory that tells us that the phase is fixed. So it's showing, in terms of its output, it's showing everything that a phonon laser ought to do. I'll say quickly how it works. It's an effective mechanical backaction. It comes because the damping somehow becomes negative. So when you have an SET, a single electron transistor that's moving, then it's going to charge and discharge a little bit as it moves through each cycle. And there's going to be an offset, a delay between the motion and between the charging because the tunnel barriers are a little bit opaque. The phase difference between those two tells us whether the damping is positive or negative. If you work this out carefully, then you can see that the slope, whether the sign of the damping depends on the slope of the charge versus displacement. If you can arrange things so that it has the slope becomes negative, which is a little bit non-intuitive, but can happen, then the damping becomes negative as well, and that means that you have an oscillator. So it's a result of the feedback between the charging and the motion. Okay, I have a couple more minutes, so I'm going to tell you, I think I have a couple more minutes. I'm going to tell you about an experiment that we did to look for another characteristic of a laser, which is amplification. And what we did is, again, copying something from quantum optics, to look for injection locking. So injection locking in a laser works like this. If you have an oscillator, actually any oscillator, it doesn't have to be a laser. If you inject some weak seed tone into this, the oscillator's phase will follow this seed tone, and the entire output, which can be much larger than the input, tracks what's coming in. So this is an amplifier. And we implemented this by sending our weak seed tone to the gate and then looking at what comes out of the spectrum analyzer. And what we see with very weak injected power, then you have some broad noisy signal coming out of the fridge. So this is just the free running behavior of the oscillator that is noisy and fluctuates because of charge noise or impurities on the surface or whatever. But as we turn up the power, then what you can see is that the output power is starting to collapse onto the injected signal, showing that it's tracking the frequency of what's coming in. And if you turn the power up high enough, then the entire output of the oscillator all goes in the same frequency of the seed tone that you're sending in, showing that it can lock to a very weak force. So this tells you that you have that it can track the force. What we also did, we looked at the spectrum, which is more complicated than you would expect. There's this very interesting sideband that appears as you increase the power. I'm not going to talk about that except to refer you to this paper and to our own paper, in which we show that this is a consequence of classical squeezing of the emission. And to summarize, what I hope I have convinced you is that there is an analogy between a laser and a mechanical resonator coupled to a single electron transistor, and to show three particular similarities, which are classical coherence, amplification demonstrated by injection locking, and mechanical squeezing as well. Thank you for your attention.
Okay, thank you very much for the excellent talk. So now the talk is open for the questions. Okay, so let me start.
Okay.
Okay. So if we think about this kind of feedback effect, I think that the response time of the electron system is very important. I mean, if it's too short, I think you cannot expect such a feedback. So probably it corresponds to some tunneling rate. So can you comment on that?
Yeah, that certainly ought to be true. What we in fact find is that the oscillations are actually quite generic in this device as you turn up the bias. So for not all gate voltage settings, but there's for almost any gate setting that you choose, there is a nearby value that makes it oscillate. So it seems that we got lucky here that the tunnel rate is slow enough to give this feedback. What helps, of course, is the fact that the mechanical coupling to the charge and the quality factor are both quite high, which means that it doesn't take very much feedback to overcome natural damping of the resonator.
Okay. Okay, one question from the audience. Thanks for an exceptional talk, Edward. In one side, you show the device with the 5 gates,
Yes.
which is the piece of the gate electrodes and the pitches among each other onto source and drain. Are they deposited in the same step? So asking about the fabrication, I think.
Oh, no, they have to be deposited in separate steps because the contacts have to be thicker than the gate electrodes. Otherwise, the nanotube won't suspend.
Okay, next question is by the Eddie Collin. So thanks a lot, Edward. Very nice talk. Comparing to the self-sustained oscillation states generated by blue sideband pumping in optomechanics, can you say something about the similarities or differences? For example, regarding phase, noise, etc. Thanks. Yeah.
Yes. Yeah, I mean, well, I'm sure there are many differences. I mean, one difference that that maybe is relevant is that the fluctuations, well, in both cases you have shock noise of the driving, of course, but the fluctuations of because the electrical current is fairly small, I speculate that the shock noise of the electrical current in this device perhaps has more influence than it would in in an optically pumped device. I mean, a thing that is quite nice from an experimental point of view is that it's fairly easy to get a DC bias down to the device. If we were to try to optically pump it, then well, other people know a lot more about how to do that than I do. But I think it is quite challenging to do that inside a refrigerator. So I suppose those are two differences between the two different ways of generating oscillations. Does that answer the question?
Okay. Okay. So next question is the Stanislas Soskin. The figure shows the quantum dot is, of course, is idealized. Otherwise, the current would it stopped at here.
Sorry, the question stopped.
Stopped. Yeah.
Oh, okay. Yeah. Well, so yes. So in my figure, I draw, of course, this perfect island, and that's not true. We know it's not true. We can see it, in fact, even on the slide I'm showing at the moment. If you look at the Coulomb blockade diamonds, they're nowhere like as regular as is in the cleanest devices that people make. And I think possibly that even helps us. So I think the reason for that is that you have some disorder. So the island is breaking up into more than one, which means the tunnel barriers themselves perhaps have some kind of weak Coulomb blockade inside them. And for our mechanism, which relies on the fact that the tunnel rate depends on the energy of the electrons, probably having a little bit of disorder gives you a stronger dependence and therefore maybe makes it easier to see oscillations.
Okay, and additional questions, it's continued. Okay, so he's asking about the current would have a form of periodically repeating delta spikes. I mean that in the idea of the Coulomb blockade, you have a very, very sharp spike, yeah, separating. And while the current versus time looks like modulations. So the damping characterization, the width of the layer. So can you comment that? Yeah. Why it's so, yeah. Okay, in the ideal station, I think that the Coulomb blockade spectrum shows a very, very sharp spike, yes, with some distance and zero current through that. Yeah, but you looks like something modulation. So what is I think the question is about that.
I mean, why the Coulomb blockade peaks are not infinitely sharp? Why they have this smooth dependence?
Yeah, I think so.
Yeah. Yeah, okay.
Damping plays, yeah.
Yes. Well, there's two things that contribute to the width of a Coulomb peak. One is temperature, and the other is the tunnel rate, is the energy uncertainty that comes because you have lifetime broadening. And I suspect in our device, well, at least in this curve, it's lifetime broadening that probably dominates. And again, the reason is because we cannot tune the barriers to be as opaque as we would like.
Okay, so Stanislav Soskin, can you comment that? Oh. Can you talk?
Okay. Okay. Hello.
Yeah.
Am I heard?
Yes, I can hear you.
Okay, I actually continued the question. The question was, is there possible to make some use of the dependence of the width on some external actions or whatever? Then you would have an additional means, you know, to make a back action or whatever. That same gate voltage oscillation or whatever.
That's a good question. So something like, can you
different mechanism, because you showed us just a different mechanism, and this could be one more mechanism for, you know, to play with this. Because definitely the width of the level should depend somehow on whatever, and it should depend in particular on strain or whatever, right? It's actually not a question. I'm sure that it is. It's just a proposition for your future work.
Yeah, it's a good question. Like as we change the width or the height of the Coulomb peaks, can we turn the back action on and off, for example? Is that would be the sort of thing?
Yeah. Okay.
Yes?
Okay.
I think that would be interesting.
Thank you.
Okay. We are already 10 minutes
And the talk
behind.
was perfect. Very interesting. Thank you.
Yeah. Okay. Let me ask a final question by the Andres Shevilin. So thank you for a very interesting talk. How many electrons go through the island per vibration period? Can it be reduced to 1, or how many electrons per vibrations?
It's let me think for a moment. So you're supposing that we have 10 to the minus 10 amps, then that's about so that's going to be awarded 10 to the 9 electrons per second. So so that implies that it's maybe 10 electrons per cycle, roughly. Can it be reduced to 1? In principle, definitely. Yeah, I mean, it's a good question what happens then, because then the random tunneling times would dominate the physics. I haven't thought much about that.
Okay. Okay, thank you very much. Okay, thank you very much for the excellent talk. And yeah. So, so let me close this session, and I'd like to thank all the speakers, not only today.